Okay. Okay, can you hear me? Okay, I'm a mathematician, so you will understand if my presentation is going to be much less smooth than the one of the dean. I'm not supposed to be a people person. So, well, I would like to thank Dean Ulrich for the introduction, and I would like to thank all of you for coming here this evening. I'm here to represent the division of physical sciences and mathematics that covers 5 departments: chemistry, earth and planetary sciences, math and statistics, and relevant for us today, physics and astronomy, of which Baram is a distinguished member. Now, these units serve approximately 1,500 students between undergraduates and graduates, and they're composed of 150 dedicated faculty that have an academic background that spans 6 continents. I checked. New Zealand was hard to find, but I did. And our research bridges pure and applied science. And today's presentation will highlight how advances in technology go hand in hand with the research of century-old fundamental questions like the ones that cosmology addresses. Now, this journey starts many centuries ago, but I'm going to discuss only of relatively recent advances. With the Hubble telescope that was launched about 30 years ago, astronomers were able to study what's called toddler galaxies, namely the state-of-the-art of galaxies approximately 1 billion years after the Big Bang. And this provided exciting progress, but it certainly is not enough. It's not back enough in time. And the James Webb Telescope that was launched less than a year ago, on December 25th of last year, we can dig deeper in the universe and see the universe up to, it was 200 million years after the Big Bang, to see baby galaxies the moment in which they were formed. Now, our guide in this journey is going to be Professor Mobasher, that comes from the Department of Physics and Astronomy. Dr. Mobasher earned his PhD in Durham, in the United Kingdom, in cosmology. He has several other degrees, including one in microwave engineering, which I'm told has nothing to do with appliances, and has held position at the Imperial College London, at the Space Telescope Science Institute in Maryland, where he represented the European Space Agency. He joined UCR in 2007 and is author of approximately 350 very highly cited papers in astronomy, cosmology, and such. Now, he has recently published a book that is titled The Origins, the Story of the Beginning of Everything. As the title suggests, it's the only book that you need to read. But I presume that it's also pretty thick. Now, at the end of Professor Mobasher's presentation, I invite you to join us in front of this building for the Highlander Stargazing, where the students of the UCR Astronomy Club and members of the Riverside Astronomical Society have on hand some telescopes slightly cheaper than the James Webb, and perhaps with a slightly lesser resolution that allow us, in any case, to see firsthand the universe. Professor Mobasher.
Thank you, Stefano, for a very kind introduction. And thank you for coming here tonight. I'm really honored to be able to talk to you for a few minutes this evening. And I do hope that after this talk, when you leave this room, you would be either convinced or confused, but not indifferent. So I was planning to go to the Beach Boys concert today, but then I thought I was too old to go there. Then I realized they were older than me. So that's perhaps I should have done that, but nevertheless, I'm glad to be here tonight to talk to you and just to tell you a great glimpse of the universe as we know it. So I'll start it with right? With 5 questions. And throughout this lecture, I go through these questions. The lecture is just about these questions. How far have we come? What do we know today? How did we get here? Where are we going from here? And what are the challenges? So I go one by one through these questions and discuss where we are. And by the end of this, you should be able to know the answer to many questions which you have asked, or your mother, grandmother, father, grandfather have asked. And we'll see how that would be. In particular, how did we get here and where are we going from here? So the first question, how far have we gone? So this is a brief history. If I've seen further, it is by standing on the shoulder of giants, Isaac Newton. So it's by standing on the shoulder of giants, we can actually see far, far ahead of us. And those giants started from the old Greeks, the Socrates, who basically started scientific thinking. His student Plato, they collected what Socrates had done and basically presented Socrates to the world. All the knowledge we have from Socrates today is because of Plato. And he was his student. Instead of going to Silicon Valley trying to make money, so he collected his instructors' work and presented that to the humanity. And that's how we know Socrates. Socrates, by the way, he was killed. He died because he was considered to be deceiving the youth by making them educated. So he was forced to have poison, and he died after that. And then Plato, Aristotle was Plato's student, who again worked on this and started scientific thinking about the universe. They were all moral philosophers, but scientists as well. So the first theory of the universe was the Earth-centered universe, where they considered Earth to be at the center of the universe. And that was about 2,500 years ago. So today we know it's wrong, but this needs some scientific thinking, some science, so that you start thinking scientific methodology to think where we came from. And this is where it was. So the first model of the universe was a sun-centered universe, putting the sun at the center of the universe. The beginning is the most important part of the work. That's what Plato said. And Aristotle said something even deeper than that. Be a free thinker and don't accept everything you hear as truth. Be critical and evaluate what you believe in. So don't accept, and this is especially for the younger people here, do not accept whatever people like me tell you. Just look for reason. Just think about it. Try to think independently about what you hear. And don't accept whatever the masses say, whatever your parents believe in. So just think independently. And then it was for 1700 years, the Earth-centered universe was there. And people believed in it until the time of Copernicus. So that is the guy who started the revolution, Copernicus revolution. He fought for 1700 years of thinking, of having the Earth at the center of the universe, remove the Earth from the center of the universe and put the sun at the center of the universe. Today, we know it's wrong. But he fought against 1700 years of belief. And that needs some courage, some self-confidence to be able to do that. He lived 600 years ago. So we went from here to there, from a Earth-centered universe to a sun-centered universe. It took us 1800 years to go from here, there, from Earth-centered universe to the sun-centered universe. It only took us 66 years to go from here, there. So this shows the progress we have made. This shows the progress with which humanity has made. And what's going to happen in the future, it's just anyone's guess. So you can consider, you could see the difference between these are the scales we have, and what's going to be over the next 66 years. Of all things visible, the highest is the heaven of fixed stars. At rest, however, in the middle of everything is the sun. That's Nicholas Copernicus, who believed in the sun to be in the center of the universe. And then came the time of Kepler. Kepler was the one who calculated the orbit of the planets around the Earth and calculated and showed that planets move around around the sun, basically move on ellipses, with the sun being in the focus of the ellipse. So 400 years ago, he believed in that, and he calculated that, and his calculations still, the 3 laws of Kepler, planetary motion, still is valid, and we believe in it, and millions of times has been tested. I much prefer the sharpest criticism of a single intelligent man to the thoughtless approval of the masses. I much prefer the sharpest criticism of a single intelligent man to the thoughtless approval of the masses. Johann Kepler. The same time as Kepler, it was Galileo. Galileo is just one of the greatest scientists. When you read his history, his biography, it's just amazing scientist he was. He lived the same time as Kepler did, and he invented the first telescope, and this was the first telescope and the most important telescope. I remember once I was working on Hubble Space Telescope, and I strongly believed that Hubble was most famous, the best telescope, the most original telescope. But then someone told me, have you thought about Galileo's telescope? Then I realized that no, that actually this telescope, Galileo's, was the best telescope, was the thing which started the whole science of astronomy. Galileo looked at the moons of Jupiter, and from that concluded that actually Earth is moving. Earth is not stationary, but is moving. And this was because of looking at different phases of moons of Jupiter. As you can see it here, it's drawing from Galileo. As you can see it here, the stars are the moons of Jupiter. They differ. The motion measured at different times, they differ. And from that, he deduced that Earth, the only way to explain this observation is to accept that Earth is moving, is not stationary. And he got himself into trouble because of that. The laws of nature are written by the hands of God in the language of mathematics. And this is Galileo said. So that with mathematics, we can explain the laws of motion. And this is quite amazing that through all these calculations, we see some reality, something we could see. With the rocket going up, that's based on laws of Newton. So that's the law of Newton, which works on it. But we can see it. It just lifts up from the earth. And this is how mathematics works in practice. And then Newton. The year Galileo died, Newton was born. And he was another great scientist. It is book Principia, who basically did the general theory of gravity and much more. If I've made any valuable discovery, it has been due more to patient attention than to any other talent. And I repeat this, especially for younger people here. If I've made any valuable discoveries, it has been due more to the patient attention than to any other talent. He was one of the most clever people ever lived on this planet. And he thinks this way. It's so humbling to think this way. Now, the second question, what do we know? So what do we know today? The good life is one inspired by love and guided by knowledge. Bertrand Russell. The good life is one inspired by love and guided by knowledge. Just think about it. Now, I come and ask some questions, fundamental questions. And these questions are the questions which have basically occupied human mind for many, many centuries. But today, we can answer these questions. Not only we can answer these questions, we could go and observe them. And this is the most important thing. We could experiment on it. So Galileo's telescope started the whole thing. And the Galileo's universe was just Jupiter, not beyond the solar system. They didn't know anything beyond the solar system. That was the universe. Tonight, we can see, we can look back at 13 billion light years in the universe. And I could show you the picture of the first generation of galaxies ever formed in the universe. And this is where we've come throughout all these centuries, all these years. We should be proud of ourselves. For over 50 years, the Palomar was the biggest telescope on Earth. The diameter of the mirror is about 5 meters. And it's just about 1 hour from here in Palomar Mountains. I advise you to go and see it. It's a beautiful sight. It's a fantastic place to see it. So for many years, many discoveries were done on the Palomar. today it's still functional. Still, we get data from it. And then about 35 years ago, the Keck telescopes in Hawaii. So this is the twin Keck telescope in the Mauna Kea Mountains in Hawaii. I used to go there quite a lot. I've been there over 30 times. And it's high in the mountain, very inhospitable. You cannot breathe because air is so thin. But nevertheless, you can see the sky. It's just you can see the sky as if you've never seen it. And you can see it. It's just above the clouds. And it's just a beautiful place, so poetic. It's the sunset, the sunrise, you can see it. It's just a fantastic place to be there. And with this, we have made a lot of discoveries. I'm pleased to say that this belongs to the University of California and Caltech. So these two institutions have time on the Keck. So this is a private telescope, the biggest telescope, ground-based telescope in the world. 10 meters is the diameter of the telescope. And with that, we could see deep into the sky. And with that, we could follow up all the sources we see with the Hubble and with the James Webb Space Telescope. And one reason that University of California has such a strong astronomy group is just because of this, because of access to Keck. And that's the envy of the astronomical community. And then you have the Hubble Space Telescope, launched in 1990, 300 kilometers above the Earth, and just goes around the Earth every hour. And with that, we've been able to see the deep into space and make the discoveries. The science of astronomy was revolutionized after Hubble was launched. And I'll show you some pictures and demonstrate that what it is. And I've been working on it for many, many years. And following it up, all the sources we detect with the Hubble, with the Keck Space Telescope. And finally, the James Webb Space Telescope, which was launched last December, nearly almost a year from now. Very successful launch, and now is in the orbit, and you're going to see it, how it is in the orbit. And the orbit is 1.5 million kilometers from the Earth. It went past the moon and went into an orbit we call it Lagrangian tube, where the gravity of the Earth, the moon, and the sun cancel each other out, and it could be stationary in that orbit. And it moves with the Earth around the sun, so that Earth works as a shield against the sun. And this is 1.5 million kilometers from the Earth. And it's taking these images, and it's working. This is one of the images taken, one of the first images taken by the James Webb Space Telescope. And here you see details of these galaxies. Every one of them is a galaxy here. And every one of them contains of the order of 100,000 million stars. So our galaxy, the Milky Way, is a galaxy. No, it's a medium-sized galaxy. And these galaxies are the size of our own galaxy. Each, on average, 100,000 million stars they have. And the smaller ones look at the dot. These are so distant from us that you just see a dot. So you see a patch of light from those galaxies. That is another picture, which is about 9 times deeper than the deepest image taken by the Hubble. And that means something. Hubble produced the deepest image of the universe ever seen by the humankind. And this is 9 times deeper. And you can see details in this image. The red ones are the ones which are more distant. The blue ones are the younger ones forming stars. From the color, you can see what type of galaxy it is. But what we know is that in each of these galaxies, there are thousands and thousands of millions of stars, like our sun. So this is one of the deepest images taken to date of the universe. And more importantly, not only we can see galaxies, distant galaxies, deep in space, we could study their construction. We could study the chemical composition of galaxies. And this shows the chemical composition of one of these galaxies. The oxygen, hydrogen, carbon dioxide, and all these neon and all these elements in the galaxy. This shows how evolved the galaxy is throughout the years. And that we can do with the Hubble Space Telescope. This galaxy is 13.1 billion light years away. So this means that the light left that galaxy 13 billion years ago and reached us today. So it's taken light 13 billion years to reach from that galaxy to us. Which means the galaxy we see today, which you are seeing it today, that is the galaxy which was 13 billion years ago. Which means the galaxy you see today, when the light left that galaxy, the Earth, the Sun, our own galaxy were not formed yet. And throughout this journey, all these formed. And this is what we see, what we can do. The third question, how did it all start? So it all started through a big explosion, the Big Bang. And this shows the chronological history of our universe, starting from the Big Bang at the very center, on the left, and then expanding to the right. So the universe was born 13.8 billion years ago with a big explosion called the Big Bang. And since then, it's been expanding for 13 billion years. And at each epoch, something happened in the universe. Initially, the elements forming atoms were formed, protons were formed, neutrons were formed. Then nuclear fusion happened. Then chemical elements started to form. Light came to be. The forces of nature started to be what they are. And it expanded and expanded. Today, with our telescopes, we could look back into the Big Bang at the very beginning. And this is what we do. This is what my research group does at UCR. Now, when I was writing this, I started to think about all these. And when I went back and thinking about that, I realized many of those questions were asked by my grandmother, who could not write. She was totally illiterate. But these questions were fundamental questions for her and kept asking, how did the universe start? So she didn't know the universe, but she used different words. But in her mind, it was the universe. How big is the universe? And what is beyond this? Are there other planets except the Earth? Is there life in other planets? These are the questions today we can answer. We can scientifically answer these questions. And we start with observing the first generation of galaxies. The question is, how are we going to find it? So it takes 8 minutes for the light from the sun to reach us. Therefore, when we see the sun, we don't see it as it is. We see it as it was 8 minutes ago. Similarly, if you see a galaxy, which is 8 million light years away from us, you see it as it was 8 million years ago, not as it is today. Therefore, when you go out tonight and look at the sky, you look back in time. So you can see the history when you look back. Therefore, if I find a galaxy which is 13 billion light years away, that galaxy I see tonight was the galaxy which was created at the very beginning of the universe. I can see the creation. I can see the origin of the first generation of stars and galaxies. Therefore, to do that, we have to find the most distant objects in the universe. In order to do that, we need to find these galaxies. How do we find this? With the largest telescopes we have in space. And this is what I mean. So by looking back in time, looking in the sky, you go back in time. So here you go back to the very beginning of the universe and eventually to the Big Bang, the creation of the universe. You can see the universe at that time. Not in optical, but in other wavebands. I'll come and discuss it. So with the Hubble, we took Hubble Ultra Deep Field. You can see it here. That was, for many years, the deepest image ever taken by the humankind, Hubble Ultra Deep Field. And then beyond that, the first generation of galaxies and stars start to appear. And we can start to see the first galaxy, the first star, and the first generation of all these at that time. That is about 1 billion years after the Big Bang. And we have reached that with the Hubble, and we pushed it back in time with the James Webb Space Telescope. And this shows what I mean. These are snapshots as a function of time. The left is most nearby, the right is the most distant. The red dot in the right is a galaxy which is about 13 billion light years away. And as you go leftward, you come closer and closer to where we are. And that's why you see more the galaxies, more details of galaxies, and galaxies which you see at night. So that galaxy, which is 13 billion light years away, that looks like this galaxy if it were nearby. That galaxy may not exist now, but that's the picture which we have of the galaxy at that time. And in order to do that, we did the Hubble Ultra Deep Field, the deepest view of the universe ever seen by the humankind. And this is a picture of that. Here, the dots you see, these are galaxies. The small sort of patch of light you see is galaxy, about 12, 13 billion light years away from us. Those are at the edge of the observable universe. The first generation of galaxies formed in our universe. And then they evolved, and we studied the evolution of them with time, with cosmic time. We've gone deeper since last year. A man who dares to waste 1 hour of time has not discovered the value of life, Charles Darwin. And this is indeed what I keep telling to my students. The science is moving so fast, it's so fascinating, it's so exciting that we just don't have time to sleep. Just work, just find out, because you are privileged. By now, I think I put you off. If any of you wanted to come to my group to work with me, probably you won't. But this is the opportunity we have to discover, to leave something from ourselves for the future generations. You will be judged by what you leave after you in this world. And this is what you need to do. A man who dares to waste 1 hour of time has not discovered the value of life. Appreciate your youth. Appreciate the time, the energy you have, the facilities you have to work with. How many people have tech? How many people have access to Hubble and James Webb? Just use this and discover something new. Now, let's concentrate on the James Webb Telescope, see what it is and where it came from. So there are two things I wish to mention here. Why is it in space? Two, why is it optimized to observe in a certain wavelength? We call it infrared wavelength. I mentioned that the universe is expanding, meaning all galaxies are moving away from one another. In fact, space is expanding and taking galaxies with itself. It's just like a rubber band. You mark on a rubber band and stretch the rubber. Those marked points do not move. The rubber is moving and taking those marked points with it. You mark on the surface of a balloon and blow it out. The points you mark are not moving. The balloon is moving. So space is moving and taking everything with it. So we see the universe expanding. As it does, the light from galaxies reaching us shift to longer wavelengths, which we call infrared. The shortest wavelength, among the shortest wavelength is the blue, and the longest wavelengths in the infrared. So they shift from blue to the infrared. From blue, which you see on the right, the galaxy, to the infrared as the light comes to us. Therefore, if we want to see distant galaxies, we need to see in the infrared wavelength. That's one reason why this telescope is optimized to observe in the infrared wavelengths, to be able to see the most distant objects, because the only way to see them is to look in that wavelength. And then the design has been done in the infrared, and this is why we see the infrared. The second reason to see in the infrared is that this is a picture taken in the optical band, in the visible band, and we can see details. Looking at it in the infrared, you see this. You see the heat from the body of the things. So our bodies emit radiation in the infrared. Everything does it. The telescope does it too. So in the infrared, we see a different view of the universe. You see the old stars, depending on which band you look at, you see through the dust, it could penetrate the dust, so you see details of all the observations. That is why the James Webb is optimized to look in the infrared. One, to see the most distant object. Two, to be able to penetrate and see inside the dust. And this is the part of the infrared. So our eyes are visible, are sensitive to visible bands. Longer than visible, we cannot see, but it exists. So if we look at the infrared, we see a different thing. That's why the cameras, infrared sensitive cameras, could monitor things at night, because it's not visible. It doesn't depend on the visible light. It depends on heat. And that's why it could see at night, the movement at night. And this is the usage of infrared. And this is an example. The left is the visible light. The middle is the infrared, near infrared, of the same object, pillars of creation, so-called, and the right is, again, a different wavelength. It's the same picture of the same thing, but in different bands. You see, in the optical, there are many things you don't see. In the infrared, you really penetrate through that. So those things in the optical are dust, which absorb the light, which does not let you to see inside that gas cloud. By seeing in the infrared, you penetrate through it, and you can see it in the middle image. That is what James Webb does. If you go to far or mid-infrared, you see something different. The light, the optical light, ultraviolet light from young stars are absorbed by dust and re-emitted in the far infrared, and you see the right thing. So you see star formation regions. You see the regions which form stars. Our own sun went through this at some point in its history, about 5 billion years ago. In a very dusty environment, it was formed. And the only way we could see that is in the mid-infrared or in the near-infrared to get rid of dust. So this is how we can see. This is why it is optimized in the infrared. Now, with James Webb, we can see deep into space. And we can see the first generation of galaxies and stars in the universe. So if you look at the left figure here, you see the stars which are beginning to form through heated gas. So gas is heated and collapses, and that forms stars. Then the stars come together, assemble, and form galaxies, the second one from the left. Galaxies come, merge, form bigger galaxies. And this is how the first generation of galaxies are formed. And eventually, the universe we see, the clear universe we see at night on the right. So this process takes about 12 billion years to happen. So from beginning, from when stars form, and that's 1 billion years after the Big Bang to the present time. Then from these galaxies, we get light. And as I said, the light is shifted to the infrared by the time it reaches our telescopes. Therefore, we need to observe them in the infrared to be able to see that deep into the universe. And here is an image. Again, a dusty region in the universe on the left, observed invisible with the Hubble, and in the right in the infrared, which shows how deep we could see inside that gas cloud. Many of those stars you see in the right, you can't see in the left. So by just looking at the visible light, we assume or we think that those stars do not exist. But in fact, they do. And this is why we need to use a different wavelength and see it in the infrared. We could also see the planets. We could identify the planets. And this is an example of a planet. So here is a shield called chronograph is put on the star at the center of the planetary system. And those little things moving are actually the planets. Because star is so bright, you cannot see the planets. If you go further away from the solar system, you cannot see the Earth or the planets. You just see the sun, because the sunlight dominates all the light from the planets. So if you cover the sun, then planets come up. And planets radiate mostly in the infrared, so you can see them. And by James Webb being in space, it has the resolution power to be able to see those planets. And that's why we can detect the planet and we can study it. With James Webb, for another few years, we would be able to see, observe the atmosphere of the planets, and if conditions for life exist in those planets. Another question my grandmother was asking. This is an image of the Earth and a picture of the spectrum of the Earth, of the atmosphere of the Earth. We know Earth could support life. We know that because we are here. So another planet to be able to support life should have these features in its spectra, should have those features in the atmosphere: water, oxygen, carbon dioxide, methane, and all these. These are the elements which are needed for life. For any other planet, if we are looking for life, we have to look for something, a spectrum like this, with all these elements. And that James Webb can do. It has the spectrograph, it has the resolution power, and it has the power to be able to observe that deep, that faint into the universe, into the planetary system. Next question, how did we get here? So the James Webb, the concept of the James Webb started in 1989. For reference, Hubble was launched in 1990. So James Webb started 1989. And when I went to Space Telescope Science Institute in Baltimore, I was hired to work on the James Webb. But then I basically shifted and worked on the Hubble because it was the initial stages of James Webb design and all these. And it took that many years to design this telescope. And after many years, over 30 years, and $10 billion, we now have it in space. It has 18 folder mirrors. And the reason that it has segmented mirror is that in order to send it to space, you have to fold it. You have to package it and unpack it in space. You cannot send it's the size of the sun shield, and all these mirrors is the size of the tennis court. So you cannot send this 1.5 million kilometers from the Earth. So you have to fold it and then unfold it when it gets to space, to its orbit in Lagrangian 2. And this is the comparison of the mirror with the Hubble. So 6-meter diameter is diameter of the James Webb. Hubble is 2 meters. So 3 times bigger, which means that 3 to the power of 2, 9 times more powerful than Hubble. That is what James Webb is. And these folded mirrors then unfold in space, and behind each mirror is an actuator, is a machine which moves the mirror. And by moving them, they could synchronize the mirror and concentrate the light falling on this. And then they send it to L2 Lagrangian 2, as I said, 1.5 million kilometers from the Earth. So it moves with the Earth around that orbit, so that Earth would work as a shield against the sun. And it gets its power from the sun. And this is the sun shield. So it's from 2 sides you can see the James Webb. One from the observing side, which is towards the universe, the other one in the back side, which is toward the sun. And from the sun, sunlight, it gets the energy, produces the electrical power, and works, supports the system on the telescope. And this is the deployment. So it was launched here from the Earth and then opened up, unfolded, and eventually in the orbit. And when this object is that far from the Earth, you could look at it from the Earth. That's amazing task of engineering. It's just one of the most complicated things which humankind has done. So what happens is that the command to the Hubble, to the James Webb, is sent from the Space Telescope to a center, deep space network in Goldstone, California. The command is sent there, and they have the antenna, they connect it to the James Webb. And the data from James Webb comes to California, Deep Space Network, transmitted to Baltimore, to Space Telescope Science Institute, and where they analyze the data and give it to astronomers like me. We observed it over the last few weeks. I'm involved in a project which just started last September, and the biggest project got time on the James Webb, which we are involved with. We are playing a role in it, and that's Cosmos Webb, which is basically starting observations next month in December. And that I have quite a lot of new things to tell you. Where are we going from here? So now I basically review some recent results from the James Webb Space Telescope before interpreting the results. We discovered the most distant galaxies in the universe. That is one picture of the first pictures taken by the telescope. This is basically checking all the instruments on the telescope, the resolution, the fact that all the mirrors are synchronized, could observe, and all that. And this is one of the deepest images taken the first weeks the James Webb started working. It's, as I said, 9 times deeper than the deepest image taken by the Hubble Space Telescope. And with this, you can see really the age of the observable universe. Never, ever before we were able to do this. And this is the reason that I started my talk with Aristotle, with Plato, with Socrates. That they started scientific thinking, and we are the result of it. We are so fortunate to be living in the time that we can do this. We can get results from the thing which Aristotle started thinking. And now, these days, we have the result of that. And more importantly, we could observe it. We can see it. We can touch it. You can observe it. You can observe the edge of the observable universe. You can see the galaxies. You can see the chemical composition of galaxies. See how evolved the galaxies are. How long it's taken for galaxies to get to this stage they are. And what processes is gone into them. This is another deep image which we got. And the deepest, one of the deepest images again. And on the right, you see the comparison between Hubble and James Webb Telescope. You see the middle one is James Webb. The left one is Hubble. I'm sorry, the left one is the Hubble, the right one is the James Webb, and the middle is the mixture of the two, stacking the two together to see all the details about galaxies. And you see on the right one how much detail you can see, which you cannot see on the left one, the Hubble image, because of the power and the wavelength and the resolution. This is just amazing how much information is on the right-hand side diagram. And then we have the most distant galaxy in the universe ever found. That red galaxy is one of the most distant galaxies. It was formed 200 million years after the Big Bang, which is the distance of about 13.6 billion light years from us. So the light has taken 13.6 billion years to reach us, that red galaxy. It may not be there now. We are looking back about 13 billion light years. It's basically 13 billion years ago when our Earth, our sun, our own galaxy was not here. And then we have details about galaxies, and you see how much detail you can see in a single galaxy. And this is again a closer image of this galaxy, which we found and is published now. And this is a collaboration called SEERS, which we are working on the James Webb. And putting that in prospect, so we have a galaxy at about redshift 16.7, which is about 200 million years after the Big Bang. As you go to the left, you get nearby and more nearby galaxies. So you can see that. So this shows how close to the Big Bang we have gotten, how close to the creation we have gotten, how close we are getting to understanding how galaxies were formed and how the universe was formed. There is one thing stronger than all the armies of the world. That is an idea whose time has come. Isaac Newton. That is true for everything. For politics, for economics, for science, for everything. What are the challenges? We are all living on the planet Earth. And this is our home, the planet Earth. Looking at Earth from the edge of the solar system, this is what we see. This is what Earth looks like. If someone tells you that there are 8 billion people living on this planet and we are getting close to 8 billion, one would not believe that. This is what we see. And what we see here on this and on the planet Earth is that there is no boundaries. There is no separation of people with respect to race, ethnic origin, religion. They're all unified. Unity is that the expression of this planet. We are all one And this is the expression we see. No geographical borders. That's what the Earth says. And this is the Earth we see from the center of the universe, from the edge of the solar system. And from that, we can see the Earth as it is. Two things is clear. One is this is the only home we have. This is just the single thing we have to live on. Two is the loneliness. There's billions and billions of miles around this. There's nothing, absolutely nothing. And it did indeed took us 66 years to get here from there. And this is how fast it moved. And for the younger people here, you could only imagine what is going to be during your lifetime. The sun, with all those planets revolving around it and dependent on it, can still ripen a bunch of grapes, as if it had nothing else in the universe to do. Galileo Galilei. This shows how humbling the sun is. I read it again. I know I'm running out of time, but I need to go through this because it's so fascinating. The sun, with all those planets revolving around it and dependent on it, can still ripen a bunch of grapes, as if it had nothing else in the universe to do. When I go out in my backyard and look at the citrus trees and see how they grow, I remember, always remember this from Galileo. What is it that we call it the humankind? Now I change the subject a bit so that become a bit more philosophical. What is the humanity? What is humankind? So I'm not going to do biology or go through this, but this, I'm sure all of you know, this is the double helix, that's the DNA, with all these being the nucleotides, with the chemical relations, chemical formulae of those, all of them. They match together and they form it. So this is the hereditary notion that we have, and this is where we come from. Humanity comes from. Not humanity, every living thing, whether it's plant or animals or all these. Well, what I want to mention here is this, a bit deeper. Where do these elements come from? You have nitrogen, hydrogen, oxygen, carbon, all these combined forming these. And these just happen to be in a chemical reaction which would form what we are today, the living life. Where did these come from? They come from deep in stars. Stars form, stars evolve, and through that evolution, chemical elements are formed. The two elements, hydrogen and helium, were formed at the beginning of the universe. The hydrogen you have in water you drink, that is remnant from the beginning of the universe. That was formed in a few minutes after the Big Bang. The rest of the elements were all formed in the stars, cooked in the stars. And once the stars die, they spread in the universe, in the interstellar medium, in the space between stars. And then they land on a planet like Earth, which could support life. And then life starts. And this is the kind of life which we have. So we come from the elements in stars. We are cooked in stars. All the carbon in our bodies, the iron in our blood, the calcium in our bones, all were formed in stars at some point. And then once it died through supernova explosion, they scattered in the interstellar medium, and here we are. And these are the elements in stars at the late stages of stellar evolution, which scatter in the interstellar medium. But what I want to mention here is the following, that somehow these come together and form something called our brain. And this is one of the most amazing things which we can see, we can study. The point is that all these chemicals come together and form the brain. And this is the brain which landed man on the moon. This is our brain which discovered everything I told you so far. This is the brain which makes a plane which you and your family ride on and go from point A to point B without being worried. So this is what it does. What is it? It is carbon, it's phosphorus, it's oxygen, it's a bit of hydrogen, nitrogen. So this is what makes the brain. So the question now is this. Is the world we see, what is the nature of reality? Is the world we see, is it the real world we see? Why is the world the way it is? So my question is the following, that the world we see, does it really exist, or is concocted by the impressions of our brains? Let me give you an example. You're all looking at me. So you see me as a handsome man, good looking. But then, why do you see me? Because the light gets on my face, is reflected to your eyes, your retina, it takes it to your brain, and you see me. Because of the neurons in your brain. But the neurons, the way neurons work in each of us, each of our brains differs from the other one. Therefore, the images of me, each of you see, may be different from the other one. Because of the processes in the brain differs. The point is, do I exist or you think I exist? In other words, when you have something sweet, is it really sweet? Or it has the chemicals which interact with the chemicals in your mouth and you feel it is sweet. In this case, sweetness doesn't exist as an entity by itself. It's an impression of the brain. The question is the reality what brain thinks? Because we see the reality of the world through our senses. And is that what the reality is? Or reality is something different, which really exists out there? That is the question. Reality is created by our mind. We can change our reality by changing our mind, Plato. Two truths cannot contradict one another. That's a very deep point. If there is one truth, then it has to be one truth. Two truths cannot contradict each other. In this case, science does not exist. Science does not have the power it has. And now, I'm getting to the end. The ultimate question. How did it all happen? And who is responsible for this all? We saw the galaxies forming. We saw the beginning of the universe. We saw the stars. Firstly, how did it happen? And who is responsible for it? In the answer to the question of why it happened, I offer the modest proposal that our universe is one of those things which happen from time to time. So this is the question, and I go to a deeper level. Which one came to be the first, the universe or the laws of physics? Let me explain this. Everything is governed by the laws of physics. It is laws of physics which created chemistry. I'm sorry, Catherine, I know you're a chemist, but that's the fact. Just chemistry is a part of physics. And then chemistry created biology, because all these chemical reactions basically are the basis of this biology. Therefore, everything goes to physics. Now my question is this: which one came first, the laws of physics or the universe? If the laws of physics came first, then the universe must have formed based on some laws. Then the creation of the universe was deterministic, based on the laws of physics. In this case, one day we may know how the universe was created, but we will never know how laws of physics came to be. If, on the other hand, the laws of physics came after the universe came first, then there was no law to create the universe, to govern the creation of the universe. In this case, the creation of the universe was spontaneous, just happened out of chaos. And the laws of physics were established somehow in the universe. In this case, we would never ever know how the universe was created. But one day, we may know how laws of physics came to be. Beware of false knowledge. It is more dangerous than ignorance. George Bernard Shaw. And I want to you think about this. To know that we know what we know, and to know that we do not know what we do not know, that is true knowledge. So I know it's complicated, playing with words, but words have meanings. To know that we know what we know, and to know that we do not know what we do not know, this is the true knowledge. Once we get to that stage, this we could call it education. This we could call it knowledge. And all these come through education. Why is the universe the way it is? That's the second question. Because we are here to observe it. Because if the universe was any way different from what it is, we would not have been here. Because we are here to observe the universe. We are here to see the universe. And we see the universe the way it is. Because if it were differently, we would not be here and we would have had no idea how the universe was. Why are things as they are and not otherwise? This is the question. And after all, the life's tragedy is that we get old too soon and wise too late. So if we start to think about it, if we are, especially for younger people, just value your youth, your energy, and try to educate yourself in whatever else you think. Education is not, I repeat, education is not gaining a university degree. Education is not getting good grades in your school. Education is education of mind. Education is you teach your mind to be innovative, to be independent, to be able to think. This is the education and the value of education. And this is what we can do. Sitting on this small planet, we could discover the universe through knowledge. And this is through knowledge we get from here to there. And this is through knowledge we get to build this. And this is through knowledge that we could discover the universe. We could address the most fundamental questions for the last 2,500 years. The strongest minds have thought about this. Whatever the cost of our libraries, the price is cheap compared to that of an ignorant nation. Walter Cronkite. Whatever the cost of our libraries, the price is cheap compared to that of an ignorant nation. And this is a quote by Dalai Lama. When Dalai Lama was asked, what most surprises you in the world? He quoted man. Because he sacrifices his health in order to make money. Then he sacrifices money to recuperate his health. And then he's so anxious about the future that he does not enjoy the present. The result being that he does not live in the present or the future. He lives as if he is never going to die, and then he dies, having never really lived. So, this is what is surprising. With all the intelligence we have, with all the intelligence we've discovered, the most distant galaxies in the universe, the edge of the universe, the meaning of life, the beginning of life, we have discovered that. But this is the problem, the weakness we have as humankind. What surprises you the most, the man? Because he sacrifices his health in order to make money. Then he sacrifices money to recuperate his health. And then he's so anxious about the future that he does not enjoy the present. The result being that he does not live in the present or the future. He lives as if he is never going to die, and then he dies, having never really lived. So try to live, and live a successful, a prosperous life. Try to live a successful life. Thank you.
Thanks, Professor Mobasher. Okay, there is some time for some questions before we get to our own observations of the universe.
I'd like to know, who is James Webb? Why the heck did you name the James Webb Telescope James Webb?
James Webb was a NASA administrator at the time of Apollo program. So he was NASA administrator when humankind landed on the moon. He was a controversial figure, and it's recently revealed that he did some bad things too. And they want to remove his name from the telescope. NASA decided against that. Yeah, that's who he was. He came from Army. He served NASA. He served successfully, and NASA was very successful during that time. And that's how his name comes. I don't know how they put his name on the telescope. It was a surprise because normally they name it after scientists, and James Webb was not a scientist.
So the James Webb telescope is observing the universe in the infrared, but the images we're seeing are in the visible, right? Because we're seeing the photos. How is that conversion done?
Right. So that's exactly the point. What you see with the James Webb, firstly, those galaxies which are too far, what you see is the light of the galaxy in the visible, not in the infrared. Just because it's too far away, it emits. The light you see is infrared, but in fact, the intrinsic light it emitted, which you see, is optical or visible. That's why you see it. If you see that galaxy in the optical wavelength, you'd see nothing.
Hi, wonderful lecture. I wanted to know why the mirrors were in the shape of a hexagon and not any other type of shape.
Because if it were a circle, you would have had gaps between the mirrors, and that's unacceptable. Because of the design of the telescope, the way it unfolds and folds, so that was the thing. So that's, yeah.
Really inspiring talk. So if we think about it, imagine the balloon is continuously expanding. Where's the position actually the Earth located in those big balloon?
Right.
I said because the telescope right now one position located, and future if we are able to like located 1 billion years away from Earth, could we actually trace back the whole history of the universe?
Right. So let me reflect your question in a different way. So we are here observing people in a galaxy which are 13 billion light years away. So we see that galaxy and those people as we are on the Earth. We think that they are at the center of the universe. They are close to Big Bang. Okay? Now, when those people look at our own galaxy, they think we are close to the Big Bang. So at the same time, both think that the other galaxy is close to Big Bang. So this means that every point in the universe can be considered as the center of the universe. You can be the center of the universe. So every point is like that because the universe firstly is homogeneous, is isotropic, and secondly, when Big Bang started, there was no space. So the space started at that time, and everything grew from that. Well, in principle, you could do that, but it's hugely difficult because there are matter you don't see, and the galaxies just many of the galaxies, the vector is moving away from each other, so everything is moving away from one another. So getting them back, yes, you could basically eventually get them to a point, but what is a point? So. They do. That's right. That's how you study evolution of galaxies. So what you do, you see galaxies at different time frames from us, and then compare the properties of galaxies. So essentially, you look back in time, the properties of galaxies as a function of time, cosmic time. That's how we study the evolution of galaxies. And when we go too far into the past, then we get to the point when galaxies were formed. And then we study the formation of galaxies. Yes, we could build the cosmic time through the evolution of galaxies, and we can study evolution of galaxies through cosmic time through this. Let me give you an example. If you say how a palm tree grows to become this size, if you want to study the evolution of the growth of a palm tree, there are two ways to do it. You plant one today and sit by it for 50 years to see how it grows, or see different palm trees at different stages of the life and compare them. This is what we do. There are different ways to see how it is. So further away you go, younger they are, because you basically go back in time. So when you go further away in the universe, you get younger and younger galaxies. So galaxies, 13 billion light years, 12 billion light years, they are the youngest galaxies because you basically go back in time. So that's one way. For nearby galaxies, you just study their colors, the amount of stars they form, because all the stars don't form stars. All galaxies don't form stars. So you study the stars they form from the blue light the galaxies have, and from that you could estimate the age of the galaxy. The type of the light, yes. Type of the light, yes. It tells you how far it is, and the color of the galaxy, which is the difference between light and different wavelengths, tells you the age of the galaxy and other properties. Yeah.
Okay, one question here.
Thank you, sir. I didn't quite hear you, but you mentioned your research project, your current research project, and saying that it involved the telescope.
Right.
And I was curious to know if it could be easily stated what kind of hypothesis you hope to test with the images that you will get.
Yeah, we do. I do many different things, and with the James Webb, and I did it with the Hubble. With the James Webb, we look at the most distant galaxies in the universe. So the aim is to find the most distant galaxies, maybe 100 million years, 200 million years after the Big Bang. Then what I do, not my colleagues, but I try to do this, study properties of those galaxies. I'm not interested in finding 100 million or 200 million after the Big Bang. So it's all the same. It's very short time. And I study the properties in galaxies, the environment inside galaxies, and how, under what conditions the galaxies were formed, the environment of the galaxy, and all this. I study that. Also morphology of galaxies, how galaxies get the form they have. Throughout the age of the universe. What is the origin of the morphology of galaxies? How are stars formed throughout the cosmic time? These are the kind of projects I do, and these are all possible with the James Webb. The distribution of mass of galaxies, calculate the mass of galaxies, how massive the galaxies are, what makes the mass of the galaxies. These are the kind of projects I do.
Okay, I guess we have time for two quick questions, and after that, Professor Mobasher will actually stay here if you want to have a one-to-one question.
Hi, you mentioned the expansion of the universe causes redshift. I wonder if you see a star that is red, how do you know it's an old star or just a young star that happens to be red?
When we see a star which is red, how do we know it's old star or a young or a
young one? Like whether it's
so
affected by
if a star is red, if a star, there are two reasons a star could get red. One is old, two is in dust, because dust absorbs the light and emits it in the redder wavelength. So these are the two reasons. The third one, more complicated one, is very, very evolved. In other words, we astrophysicists tell it metallicity. The amount of heavy elements is large in the star. That makes a star red. So there are three reasons making a star red: age, metallicity, heavy elements, or the dust.
Do we have time for just one last question?
In one of the illustrations, it looked like the telescope was orbiting L2. Is it orbiting L2 or is it stationary in L2? And if it's orbiting, how come?
Yeah, it's basically moving behind the Earth and at the same time orbiting there. But it's just orbiting around, say, in a small sort of orbit around L2, but it's moving behind the Earth. So it moves with Earth. It's basically and so that Earth would shield it against the sun.
Okay, well, I would like to thank Professor Mobasher again and the audience for being so attentive. Thank you.